Do you have questions on any of these? Do any of them stand out to you as obviously correct, obviously incorrect, maybe correct, maybe close to correct? How did you solve these? How did you figure it out? Do you want to start? Use your notes. Tell me how you used your notes, because I'll be honest, I've messed up your notes a few times this semester. Not yours specifically, but in general. Made some weird clerical errors that have made the notes I've given you a little messy and hard to use. So how did you navigate your notes to solve it? And which one did you do, Jordan?
I did that one.
This one.
I looked at this guy.
Your reaction diagram, starting with the alkyne. That's what you started with.
Yes. And I saw that you had added a carboxylic acid to that one. And
Good.
that is this top one, so that I use the same.
Now, you're looking at this conversion from 1-butene to propanoic acid. I don't see an aromatic ring in there. How did you know that this was going to actually work?
Because there's a terminal.
Okay. I've got a terminal alkyne, and I had reference to terminal alkyne. So it doesn't really matter what the carbon chain is. That the rest of that R group can look very different, but I've got the alkyne forming a carboxylic acid. By the way, that wasn't a trick. That was just a reminder that functional groups have abbreviations. Did you guys recognize that abbreviation from what, I think like week 2 of the semester, week 3? This was not me trying to trick you into not noticing that it's a carboxylic acid, just reminding you that there are abbreviations. Follow-up question, does this oxidative cleavage only work on terminal alkynes? I only gave it to you on a terminal alkyne, but does it only work on terminal alkynes? What if I had 2-pentyne? Does oxidative cleavage become ineffective? What do you think? This is a challenge, right? When I give you a reaction diagram that has one starting material that's terminal and one starting material that's internal, you have to decide what implications that has. Is one of the implications that it is ineffective on an internal alkyne? Well, don't forget that when we cleaved the carbon-carbon triple bond, we formed a 3-carbon carboxylic acid, but we also formed a 1-carbon carboxylic acid. You see that in your notes? So if I cleave the carbon-carbon triple bond, I should form a 3-carbon carboxylic acid. And now I have a different carbon chain, so this should be a 2-carbon carboxylic acid. The 1-carbon carboxylic acid is unique to the terminal alkyne. It's weird to call it a 1-carbon carboxylic acid, but that is what it is. It's carbonic acid. But if you do oxidative cleavage on a terminal alkyne, that 1 carbon on the end becomes carbonic acid. You do oxidative cleavage on an internal alkyne, you could just get 2 carboxylic acids. This is one of the challenges of my reaction diagrams. They try to sum it up as nicely as possible, but sometimes there's information that gets lost, like how an internal alkyne is also reactive. Okay, great. Great work. Alkyne becoming a carboxylic acid, oxidative cleavage. And there's 2 different ways you can do that. If you have access to ozone, you can bubble ozone through your reaction. If you have access to potassium permanganate, you can boil your reaction with potassium permanganate. Jordan?
So why did you not draw both off? Because it's a cleavage.
So why did I not show the other one? Well, it's a terminal alkyne. So the other carbon that's produced in this oxidation is carbonic acid, which doesn't exist for very long. It decomposes really quickly, and it leaves your reaction as water and carbon dioxide. So there is a missing product, carbon and water dioxide. Water and carbon dioxide are byproducts here because of the carbonic acid. They're just not the major product. That's a great question. I didn't show everything that formed, but the only way to form this is if there's something else that forms and I'm just ignoring it.
And so we're okay if we, my brain, I need to show that.
Sure.
Is that fine?
Yeah, okay, so one way that you'll have to approach this on the final and on the upcoming unit test is you'll have a reaction roadmap. It's very similar to what we're doing here. There are reagents that need to be filled in, and there are products that need to be filled in. And you have to be able to determine the missing piece of information. In fact, another thing I like to do is leave one of these blank, and you have to figure out the starting material that they all come back to. If I show you something like this on the final, and I ignore the carbon dioxide that is produced, you have to just recognize the only way this can form is if I also form carbon dioxide. I just must not be paying attention to it. But if I ask you to fill this in, give you an alkyne and reagents for oxidative cleavage, I probably would be fine with you ignoring the carbon dioxide and water, unless I make it clear that I want to see both cleavage products. But if you showed me the carbon dioxide, if you showed me carbonic acid, you showed me carbon dioxide and water, totally full points. I know that can feel a little vague, confusing, which way do you go? But this comes down to the idea of a major organic product and less important byproducts. Okay, let's see. Did you give this one to Selena? Did you notice this in your notes after she gave it to you? So how would we tackle this problem? Once again, I'm starting with an alkyne, so I can look at my reactions that have alkyne as a starting material. And I want to make an alkene. There are two reactions that took alkyne to alkene. They were both partial hydrogenation reactions. Okay, but sodium in ammonia, or metal in ammonia, gives a transalkene, and hydrogen with Lindlar's catalyst gives a cisalkene, and this is neither. It's neither cis nor trans. It doesn't apply. So how do I know if sodium in ammonia works or if hydrogen with Lindlar's catalyst works? Either one would work here.
On the diagram, the Lindlar's catalyst option, like it rearranges spatially.
No. It gives a cisalkene. Did I screw up my diagram? I mean, it wouldn't be the same time.
Like
Wouldn't be the.
and shape-wise, like spatially.
Okay, on the diagram, it goes from 2-butyne, internal alkyne, to cis-2-butene. That's just as much of a spatial rearrangement as forming trans-2-butene. What you're pointing out is with an internal alkyne, partial hydrogenation leaves me with cis or trans alkenes.
And both are like.
Because I'm going from sp hybridized to sp2 because I'm going from alkyne to alkene, and because it's internal. So by adding hydrogen to both carbons, I will have a cis and a trans possibility. But it's not that both are possible, Jordan, from the reagents. Only one reagent takes an internal alkyne to cis alkene. Only one reagent takes an internal alkyne to trans alkene. Is this an internal alkyne? Is this a cis alkene? A trans alkene? So the regiochemistry and the stereochemistry here are specific and important. Regiochemistry, internal. That impacts the stereochemistry, cis versus trans. Regiochemistry here is now different, terminal. So cis and trans can't form, so cis and trans aren't something I have to consider, which means either one of my reagents works.
But internally, only the limpers would give us the cis.
Correct.
Okay.
And to be fair, let's look at it this way. If black is my original hydrogen, then forming this by sodium and ammonia would place my two new hydrogens trans to each other. The sodium and ammonia is a trans addition reaction. But if I ran this by hydrogenation, H2 with Lindlar's catalyst, then my two new hydrogens get added to the same side. How can I tell? I really can't, because it's not a stereoisomer alkene. So I can't tell which hydrogens got added where when I look at the actual product, because whether the new hydrogens added trans or cis, it leaves me with the exact same product. I could study it. Notice how the original hydrogen ends up either trans to the phenyl group or cis to the phenyl group. There is some coupling constants that now can be studied in NMR. And if I were to do an isotopically labeled experiment, for instance, instead of sodium and ammonia, I run this in sodium with deuterated ammonia. Do you guys remember what deuterium is? It's H2. So it's heavy hydrogen. It's the isotope of hydrogen that has a neutron. If I run this in deuterated ammonia, I don't add hydrogens, I add deuterium. And now I only get one hydrogen signal in NMR, and I can actually study that NMR signal. Or if I run this with D2, deuterated hydrogen, I add deuterium Sn, because deuterium is chemically hydrogen. So it does the same chemical reactions that hydrogen does. But it is not NMR active in the same way that hydrogen is. So I can now test my experiments with isotopically labeled elements, and I can actually determine using NMR coupling constants that this hydrogen is in a different spot. That'd be the only way to do it. But if I ran this all with hydrogen, either way, I get the same product. You guys are nailing the questions, by the way. I expected this one to be the hardest because I didn't show you how a terminal alkyne partially hydrogenates. I only showed you how an internal alkyne partially hydrogenates. So I expected this one to be the hardest. But you're nailing the questions about regiochemistry and its impacts on stereochemistry. All right, from this reaction, this is actually styrene. If you polymerize this, meaning you attach these carbons in sequence, you get styrofoam. Styrene to 1-chloro-2-phenylethane. I'm adding H and I'm adding Cl. So is HCl a good reagent for me? Why does it need something else? If this is a base and it gets protonated by my acid, the positive charge will be left on the more substituted carbon. Also, the positive charge is left on the carbon adjacent to a resonance contributor. So this is a resonance stabilized position. We call it benzylic. That's where the chloride would then attack, which means that this is not Markovnikov. This product is anti-Markovnikov. If we track where the hydrogen added, we see the hydrogen added to the carbon with less hydrogen. So HCl will not give this product. What change can I make to get this product? Kirsten? I need peroxide. How would you write it? H2O2. ROOR. Generic works fine. Do you know what doesn't work fine? That is generic. Saying HX. HX can happen here with ROOR, but I specifically need chlorine to be added. So I need it to be HCl for this specific example. But my peroxide could be anything, so ROOR works fine. You see the distinction between that? This is anti-Markovnikov HX, but I need my X to be chlorine, so I'm going to specifically say HCl. Great. All right, going up, we have our alkene. What type of reaction are we running by mixing it with bromine and water? Name for the reaction? Halohydrin. It's halogenation in a polar protic solvent. How do you feel about the regiochemistry? Bromine was added to the primary carbon, water was added to the secondary carbon. Does that agree with what you expected? Does it not matter? Was it random and they just guessed right? How does the regiochemistry line up?
I agree.
Good. The halohydrin, the haloether mechanisms, they have the intermediate with the halonium ring. And that halonium ring gets attacked at one carbon or the other. But when those carbons don't have equal substitution, one carbon is more likely to be attacked. It's more likely to be attacked at the more substituted carbon, because that carbon is already breaking its bond to bromine more, because that carbon can hold a positive charge better. So the regiochemistry is specific. It has to be a more substituted alcohol, a less substituted halogen. Good. What was the last one? Taking the alkyne starting material. What reaction are we running by adding mercury sulfate, sulfuric acid, and water? It's hydration. And this one specifically is called oxymercuration. It's similar to the alkene oxymercuration reduction, but it doesn't have a second step. It doesn't introduce a reducing agent. So it's just oxymercuration. It's a Markovnikov hydration, which means on a terminal alkyne like this, it will always add hydrogen to the less substituted carbon, oxygen to the more substituted. it gives us a ketone. One thing I didn't give you guys about the alkyne hydration reactions. I want to make one small note. Are you guys okay if I clear this? You got it all? Alkyne hydration does not form the ketone or the aldehyde directly. So in this example, where we form this ketone, it gives us what we expect, which is it adds hydrogen and OH. It adds H and OH, which is hydration, H2O. Do you know what we call this functional group? This is on your table of functional groups. It's not a carboxylic acid, because that would require a CO double bond with a COH. This is just called an enol. It's not an alcohol because it's an alcohol attached to an alkene. So it's specifically an enol, and enols are able to go through a process called tautomerization, which means that they can structurally interconvert. This enol is a structural isomer to this ketone. And it uses acid to do that structural tautomerization, that structural isomerization. Oh, I can't say it. Isomerization. That's acid catalyzed. If we run the same reaction, the same starting material, but we go for the aldehyde, anti-Markovnikov hydration, this also runs through an enol. But this tautomerization is base catalyzed. This isn't something I'm going to ask you guys to be able to show for the final or for the unit test, but it is something I want you to recognize, especially if you go on to take OChem 2. We will do these mechanisms. We'll show the interconversion between enol and ketone, enol and aldehyde. It's actually not that challenging at all, but it just doesn't relate well with the rest of the chemistry we're doing this semester, which is why I don't focus on it this semester. So I want you guys to recognize we're hydrating by adding H and OH, just like we did with an alkene. Add H to one carbon, OH to the other. But these enols that form are not as stable as just a normal alcohol, and they are reactive to the conditions they're formed in. All right, questions from that roadmap exercise? Do you like those? I do. I want to show you guys somewhere that I got a lot of inspiration when I was becoming, writing my own exams. This is the professor that I TA'd for in grad school, and she posts all of her exams online. So you've taken my midterm. This is one of her midterms. You can see that this is a lot of short answer. It actually has no multiple choice. When I learned that most of my students are taking this class to go on and take an entrance exam, like the DAT or the MCAT, that's all multiple choice. So I knew I needed to teach how to do multiple choice. This is how the professor, I really admired her teaching style and the way that she covered material. This is how she would cover, have you learned the reactions? Here are starting materials and reagents. Show me the products. No guides, no, this is how many products you're going to have, this is what it will look like. Then the next page, here's starting material, here's the product, give me a reagent that completes the reaction as shown. You just got to have it down, no multiple choice. Nowhere else on the exam where you might be able to actually squeeze out some of these answers. If you guys have not already, I am going to maybe spoil this a little bit. I want to give you a sneak peek at what the final looks like so that if you've not already looked at it, oh, that's a problem, huh? I thought I uploaded it. Was that my OChem 2 class that told me this was missing? Or was it you guys? OChem 2 then. Sorry, I didn't realize you can't actually look at the final. As I struggle to upload this with all of you staring at it, I'll explain what you're going to see. I don't like to do those questions that are just show me the product from 10 different reactions or fill in reagents from 10 different reactions. What I've decided that I like doing is a roadmap where I can have you show me products that are missing from a reaction or show me reagents that are missing from a reaction, but it just keeps going and it's all related to each other. I like that because it demonstrates to you synthesis, that organic chemists will start somewhere and take it to a very different place. And it shows that a lot of things are connected. There's a lot of different avenues you can go down. For example, how many different ways did we go from that alkyne? 3 different directions. And from the alkene, 2 different directions. So from here, it shows you all of the different things that you can do in a chemical reaction. Sometimes my roadmaps are harder than others. Sometimes I make one part of the roadmap extra hard and then that just throws all my students off. But the nice thing about a roadmap is you might miss something somewhere, but that doesn't mean you're missing it the whole way through the roadmap because you've got more context clues further on to learn from. One thing that maybe is the most challenging is a spot like this, where you've got 3 blanks in a row. That is a true synthesis problem for you. I'm not giving you the guardrails there. You have to be able to figure out what could this have come from and what reagent would be necessary. And that same thing it could have come from, how did I make it from this? I've got a terminal alkyne, and I need to get to an allylic halide. What conversions are possible, and what conversions set me up well for this next step? That's a multi-step synthesis. We're going to practice them next week. We're going to practice doing multi-step synthesis problems.
Could that have multiple answers? Or
Yes and no. I don't want to give away the answers because I want you guys to still try solving this as you prepare for the final. But sometimes there are different routes that you can go through. Sometimes there's really just one set of reagents that's going to work.
do you have the key posted as well too?
I only had the key until a minute ago. I'm not sure how I did that. Okay. Good stuff. All right, our activity for today is covering substitution and elimination reactions with alkyl halides. We're going to learn the last of the mechanisms for our class. We're going to learn mechanisms for reactions called Sn1, Sn2, E1, and E2. We're only going to cover the mechanisms for alkyl halides, although these mechanisms can also apply to alcohols. We're going to talk more about alcohols next week. You're welcome. You're welcome. That was a good number. I only had one left. So nobody else show up. I'm just kidding. Okay. At the top of our worksheet, we have a variety of different chemicals. You'll notice that some of these chemicals have negative charges, some are neutral. And you'll notice that the header says bases and nucleophiles. I'd like us to quickly review. What is the difference? What is the similarity? Definition of a base? Well said. It depends. You want to give me one?
Well, I mean, oh gosh, I need to look back over my notes, but there's the two different ones, one that relates to hydrogens and one that relates to electrons.
There's actually three.
Okay,
Yeah.
at least two
Yeah.
I can think of off the top of my head, and the one that relates to electrons is the nucleophiles.
True, exactly. So nucleophile already is a word for a certain type of base. This was our word for a Lewis base. And a Lewis base centers around how electrons are being shared, how electrons are changing. A Lewis base is an electron pair donor. That is something that has an electron pair and uses it to form a bond. All Lewis bases are Bronsted-Lowry bases. But not all Bronsted-Lowry bases are Lewis bases. Bronsted-Lowry base involves hydrogen. What does it do with hydrogen? Accepts it. This is a hydrogen ion acceptor. Let's consider this example where ethanol and sulfuric acid react to give protonated ethanol and bisulfate. And actually, let's not show sulfuric acid. Let's just start with hydrobromic acid to form bromide. Can you see how ethanol is serving as a base? It's accepting a hydrogen ion. Can you see how it's acting as a nucleophile as well? It is taking one of its two lone pairs and it's donating that lone pair to make a bond. It's an electron pair donor and a hydrogen ion acceptor in the same instance. It is both a base and a nucleophile. Generally, though, we say that if it is being a base, that's its classification. All right, then I want you guys to take this compound, which we will abbreviate from time to time as TBuO-, tert butyl group, tert butoxide. And if we look at this, reacting with something that is not very stable, a primary carbocation. I could have drawn this as a line, just a stick, because a 2-carbon chain is pretty short. I didn't want to. It looks a little awkward drawing a 2-carbon chain, just a little stick. But it could have been a stick with a positive charge. There are two things that might happen here. One thing is tert butoxide might act as a base. It accepts a hydrogen ion and goes from tert butoxide to tert butanol, which means that my carbocation is serving as the acid. It donates a hydrogen and becomes an alkene. Elimination. Actually, I'll be honest, I don't know why I put the carbocation. I shouldn't have done that. That was a mistake on my part. I'm going to make it one bromobutane. Sorry, one bromoethane. Sorry. It works either way. Either way works fine. But this, I think, will make a little bit more sense. This also generates some Br minus, now that I've changed that. Both of them do. In the reaction above, ethanol acted as a base and a nucleophile in the exact same step. Now, in this reaction, tert butoxide can act as a base, and it can run elimination. Or it can act as a nucleophile, and it gives substitution. So these reagents that are able to donate electron pairs might donate electron pairs and take a hydrogen, giving us an elimination product. They might donate an electron pair to substitute another group, giving us a substitution reaction. If this acts as a base, the reaction has gone through elimination. If this acts as a nucleophile, the reaction goes through substitution. Unfortunately, the same chemicals can react in more than one way. An analogy that I like to give for this is if you are hiking in our beautiful Utah mountains and you find yourself in a valley, you're not quite sure which way to go. Either way, you're going to have to climb out of this valley over one hill or the other. If they look like similar heights and they look like similar amounts of energy needed to climb out, which way are you going to go? One day you might wake up and go one way. If it had been another day, you might have woken up and gone the other way. In terms of a ball rolling across the hills in that valley, if I pump energy into that ball, which hill is it going to overcome first? Well, whichever one has lower energy. But if they're at very similar energies, I have some good likelihood of the ball going over either direction. That is what we're seeing here. Our reagents have more than one way that they can react. Depending on the orientation that they run into each other with, I might get one reaction or the other. But luckily, not everything is equally good at being both a base, taking hydrogens, and being a nucleophile. So we're going to create categories around these groups. Your first group is called strong base, poor nucleophile, or bad nucleophile, or weak nucleophile. And that is strictly tert butoxide. I want to show you guys another way that we can write tert butoxide. You'll notice there is no counter ion there. If you go into a lab that has tert butoxide, you will always see a counter ion. Sometimes you'll see tert butoxide written with potassium. Do you remember how we can write these in either orientation, either direction? Some people look at potassium tert butoxide on the bottom there, and they say, why is TBU okay? Like, they don't interpret that as oxygen and potassium. Just pointing that out. If you see that potassium, cool, positive charge. That only tells you that the oxygen has a negative charge. All right, we're saying that this reagent is good at taking hydrogens, but it is not that good at bonding to a carbon and running substitution. Why? What's holding this oxygen back from running substitution reactions? What makes it a poor nucleophile? It's size. We call tert butoxide a bulky base. With those 3 methyl groups, it takes up a ton of space, which means that it brings with it a lot of fight for physical space, steric strain. And introduce my first Instagram reel for you guys for the day. Here is an animation of a substitution reaction where you can see a nucleophile coming in to join a carbon and a leaving group leaving. It gets into this high energy transition state before falling down to the other side. The nucleophile here, hydroxide, is very small. It doesn't actually take up that much space. So when it comes close to the carbon, it doesn't have to fight for space because it doesn't take up a lot of space. If I substitute OH for O, C, CH3, 3, I'm now taking up a ton of space, and that nucleophile has to fight against all of the rest of the carbon chain surrounding it. Being bulky makes it bad at getting close to that carbon. Makes it bad at being a nucleophile. Okay, our next group. You guys see that on your chart, how that is kind of on its own on the left-hand side? Our next groups are weak base, strong nucleophile. That is cyanide, azide, sulfide, bromide, iodide. These reagents don't want to take a hydrogen. If they do take a hydrogen, they give it right back. They're not as, well, and that's not totally true, but they're not as good at taking hydrogens, but they do love to share their electrons. Carbon, we know, loves to share electrons very well. Nitrogen's not so bad itself. Sulfur is good at forming bonds. Bromide and iodide, those are on the larger side of the family. They're not good at being bases because they're very strong acids, but they'll share their electrons. Our next group is weak base, weak nucleophile, or weak base, poor nucleophile. I'm sorry, I'm not always very consistent with the way that I just differentiate between poor and weak. Yeah, poor and weak are saying the same thing. You could also say strong and good. Those are the same level as well. things that are not good at being bases, but also not that good at being nucleophiles. Chloride, water, and alcohol. If you want it to take a hydrogen, it's not going to do that very well. If you want it to bond to a carbon, it's not going to do that very well. So what's the last category? Strong and strong. Things that will rip away a hydrogen and will bond to a carbon quite easily. And what do you see in there? What types of groups are we calling strong bases, strong nucleophiles? Yeah, something that is not good at taking a hydrogen. Something that is not good at bonding to a carbon. Or at least relative to these other things that bond to carbon very easily. Lots of oxygen, but didn't weak base poor nucleophile also have a lot of oxygen? But there's a difference. Yeah, and if you remember in Caryo, we said that charge can help you predict acid-base character. A more negative charge means a better base. So water as a conjugate base becomes hydroxide. That's just a better base than water. Alcohol has a conjugate base, alkoxide. It just depends on what alkyl group you have. Meth oxide, eth oxide, tert bute oxide. Eric. Change out that R group for really anything other than tert butyl. And you've got an alkoxide. So it's not just oxygen groups, it's negatively charged oxygen groups. And what? Sorry? No, because chloride was not good at being a base or a nucleophile. Cyanide, azide, sulfide, iodide, bromide, very good at being nucleophiles and doing substitution, but very bad at taking hydrogens. So it's not just anything negatively charged is a strong base and strong nucleophile. These negatively charged carbons. This is our deprotonated alkyne. Remember how we used that for alkylation? Alkylation is a substitution reaction, and it can run substitution because it's a good nucleophile. It's not very often that we form a negative charge on a carbon, but that's what this is indicating, a negatively charged carbon. If you have a negatively charged carbon, it is great at donating those electrons to other carbons, but it will also rip away any acidic hydrogen it can get its hands on. In OChem2, you'll generate a number of negatively charged carbons. In lab, you'll even generate something like this. And if it has any water present in the apparatus at all, it rips a hydrogen away from the water, sometimes violently. I had a lab across from mine in grad school that disposed of a reagent like that, not carefully. They just dumped it in their organic waste, and it lit on fire because it rips away hydrogen so violently, it causes other things to ignite. It releases so much energy. And they couldn't turn off the sprinklers, so the whole building flooded for 24 hours. Like the fire department showed up and they said, we don't know how to turn off the sprinklers. Fun. Jordan, I cut you off.
Does R stand for like just carbon chains, or could other things be present in it too?
You know, unfortunately,
I understand what you're saying in this example, but just in general, does R?
Generally, R will mean carbon something unless specified what it is being used to represent. So in this case, R means a carbon structure, but R can definitely be used to represent hydrogen, OH, a benzene ring, anything. Yeah. It depends on context. In this context, it's negatively charged. There is one negatively charged carbon that is not a strong base. On our list. Where is it? Cyanide has a negatively charged carbon, but because of its triple bond with the nitrogen, it stabilizes that negative charge better, so it's not as strong of a base, but it still would love to share that lone pair that it has and act as a nucleophile.
Why is chlorine not a strong nucleophile?
Why is chloride not a strong nucleophile? Good question. The distinction here comes down to polarizability, which is, of course, an ion's ability to polarize itself. As a negatively charged ion, it doesn't have any inherent partial charge. It has a net negative charge, but it doesn't have any partial charge. But as we go from a smaller atom to a larger atom, or I should say a smaller ion to a larger ion, the nucleus inside the ion can find itself isolated towards one side of the electron cloud. What makes up more of an atom, the electron cloud or the nucleus? Nice. The electron cloud is 99.9% the volume of the atom. So if the nucleus ever finds itself out on the far edges of the electron cloud, well, now there's a strong partial positive from the nucleus relative to the rest of the atom, the rest of the electron cloud. But chloride can't really do that. So iodide and bromide, by being more polarizable, can actually create these stronger partial negative regions that it can use to butt up against something and run substitution. But chloride and fluoride being smaller, you'll notice fluoride's not even on the list. Chloride and fluoride being smaller can't polarize themselves quite as much, making it harder for them to actually donate their electrons. All right. We're focusing on alkyl halides today. And I want to rule out a couple of alkyl halides for you. We will not look at elimination or substitution of aryl halides or vanillic halides. And I have never seen an sp-CX bond. I don't know what name you'd call it, the alkyne to a halide. I've never seen it, but you won't have to worry about it. So the only ones we'll be dealing with are alkyl halides. We will not run substitution until OChem 2 on aryl halides or vanillic halides. We can talk about why MO theory tells us that we can't. But for now, I just want you guys to recognize only elimination and substitution in this unit on sp3 hybridized atoms. All right, we've got this next part on our worksheet, reactivity of alkyl halides. You can see on one side, I've put poor carbocation stability, and on the other side, I've put large steric strain. Well, what kind of alkyl halides can I have? Carbons that are sp3 hybridized, bonded to halogens. How many different ways can that happen? Could be a methyl carbon, a primary carbon, a secondary carbon, or a tertiary carbon. Those are all sp3 hybridized. They're all distinct from each other. And they're all alkyl halides. They don't fall into these categories. In that range, methyl halide up to tertiary halide, which would have poor carbocation stability if a carbocation formed from that halide? Which would have the worst stability? Methyl or tertiary? Methyl has terrible carbocation stability. Why? Just because you memorized it? Not quite resonance. It is because it's less substituted. Why does the substitution impact stability? It's got electron density around it, shielding that positive charge, donating in electron density towards that positive charge, stabilizing it. So a methyl carbocation has very low stability. A tertiary carbocation has very good carbocation stability. What end of our spectrum has larger steric strain? A methyl alkyl halide or a tertiary alkyl halide? Because again, all of that extra electron density, the same electron density that is stabilizing the carbocation is steric strain. So a tertiary alkyl halide has very large steric strain, but a methyl halide has essentially no steric strain. You guys are okay with this, yeah? That was pretty easy. Okay, do you guys want a break? Let's do about 7 minutes. We'll come back just before quarter after. Get up, move your legs, get your blood flowing, and we will keep talking about how these factors impact our reactivity, or what type of reactions we can expect.
Can I ask you a question?
Mm-hmm.
Okay, I was doing the homework, and in this one, oh sorry,
No, it's okay.
okay, this terminal added to this side, which I had drawn it out and it made sense in my brain. Why? But I feel like on our notes, which again, maybe this is me just like reading it wrong. It made it look like
Bye, guys.
it added to.
I screwed up.
Okay.
Yeah, so this terminal starting material was supposed to be used with the HX addition
Okay.
because HX is regioselective, so I wanted to show the regiochemistry. This internal was supposed
Got
to
it.
be used with
For
the
these
X2
ones,
addition
That makes, okay, I'm following.
because it's not regioselective.
Okay, because I drew it out and I was like, wait, but I'm confused. Okay,
So what I would say is
do this
from, yeah, if you can,
and put these.
I know.
Do this one. Okay.
What you notice is that 2 equivalences of halogenation leaves you with a vicinal tetrahalide.
Okay.
Do you agree what that says? Vicinal meaning adjacent carbons, tetrahalide. And that's what you drew. You drew a vicinal tetrahalide. Exactly right.
Okay.
And your mechanism looked great too.
Oh, thank you. Well, I didn't finish it, but I was like, okay,
Well, that's all you needed.
Yeah.
To prove that they're going to end up
on the same.
on the separate carbons. Yeah.
Thank you.
How are you doing?
Good. How are you?
Very tired. My finals are 2 weeks from now.
Uh-huh.
Wait, not even 2 weeks. 10 days. 14 days.
At the U?
Yeah, 2 weeks.
Exciting. So that means 1 more week of classes
Well, yeah, 1 more week.
and then final week. We've got 2 more weeks after this. 1 week of material, and then I give them their final unit test, and then we do a week of review.
You have a unit test before the final?
I do so I give 1 midterm
Okay.
and a final.
Oh, okay.
And I have 3 unit tests before the midterm and 2 unit tests after the midterm. But I don't cover any new material between the final unit test and the final exam. I used to give 3 midterms and then the final. And I used to cover material between that 3rd midterm and the final.
Yeah.
So the final would have new questions that they had never been tested on other than on their homework. Why? That doesn't really seem fair. I feel like I should give feedback first on everything that I want them to learn before I give them their final assessment. So homework is low stakes, unit tests mid stakes, exams are high stakes. I want to give them feedback at the mid stake point before they go on to the high stake. But that's just me. Not everybody agrees with that.
My friend in biochem right now, he has his last midterm tomorrow, and his
Wow.
finals a week after that.
Oh, yeah, see? So in our Gen Chem courses, we give the final unit test the weekend before finals week. So, if they were on track with the semester, the last week of classes, at the end of the last week of classes, they'd take a final unit test on that newest material, and then somewhere in the next 5 days, they have to take the final. Very little turnaround time to figure out what you missed on the unit test and master it before you see it again on the final. Not to mention, in that turnaround time, no more professor. You don't get to come to class and ask questions. You can hope that your professor is going to hold office hours during finals week. Some do, but you know how professors are sometimes. I just graded my Gen Chem lab's 2nd lab experiment yesterday. And 3rd and 4th. I came into lab and I was like, man, don't you just hate those professors that wait 14 weeks to grade your lab stuff? Or, okay, I think it was actually more like 10 weeks. I was 10 weeks behind. Not good, not good. Not fun, Some of those students were like, why do I have a D in lab? Oh, he hasn't graded anything ever.
So are you pretty lenient on if they messed up on something in their lab report, then you'll keep talking to them? Have the feedback?
Okay, so if they screw up in their data stuff, that you only get to do that once while you're in lab. But if they don't write their discussion, or if they didn't upload their graph or something, yeah, I'll tell them to just upload it. I'll dock points so they know to do it. But I'll give them a chance to redo that. But they can't fix their data. That's falsification. Mm-hmm. This semester I'm online.
That sounded so exciting.
I love Gen Chem, but I'm teaching it online this semester, and I feel like I'm doing the worst possible job I could.
Do you do 1N
No, I haven't taught Gen Chem 2 yet. I think I could do really well at Gen Chem 2 though.
I don't really like Gen Chem. I hear that again.
It's so
What's your
fun.
favorite to teach?
I don't know, I just love talking about chemistry.
Is that really your Instagram?
Yeah. But you can't see my name, so you can't follow me.
Oh my gosh, wait, why?
Because I'm in charge of your grade. That's why.
Wait, but isn't it like a chemistry account or no?
Oh no, not my Instagram.
Oh, I thought this was your.
I could make an Instagram account for my. I have my chemistry YouTube.
Yeah.
That's what I thought this was.
That's fair. Yeah. No, sometimes I'm just scrolling through Instagram and I like find video. I get a lot of chemistry reels.
Chem
No,
talk.
same.
You don't make your own.
No, I am not an influencer. This is already hard enough for me. This whole like camera setup, the influencer mic. Oh, that almost fell off. See, I'm not cut out for this.
You can be the next organic chemistry tutor.
Actually, I am already an organic chemistry professor, so I feel like I raised the bar. I've tried watching some of his videos. I get so bored. But to be fair, I get bored watching my own videos. Man, why is he going so slow? Like, I know this stuff. Just go faster. I want to see a harder example.
That's what 2 times speed is for.
Yeah, that's true. Students that watch mostly online, whether it's Canvas or YouTube, and then come in and hear me talk in person, they've told me, oh my God, I didn't realize you talk so slow in person. I'm so used to your voice on double speed, or time and a half. Okay, I want to do an exercise on mechanisms and mechanistic plausibility. We're going to do something generic. For this example, we're going to take a carbon that has 4 things bonded to it, but we're really only interested in the halogen, so I'm not paying attention to anything else. I'm going to react this with a nucleophile, but I'm not going to say whether this is a good nucleophile or a poor nucleophile. And we're going to look at the substitution. We've already played the game of spot the difference this semester. So, can you spot the difference? What change happens during this chemical reaction? What bonds break, what bonds form? Good. CX bond breaks, C to nucleophile forms. In the past, I've told you exactly how many steps this is going to happen in, but I want you to try and predict how many steps are needed. How many different ways can you do it? So Jordan, you raised 2 fingers.
Well, I actually don't know if I know how to count. You start there, and then you have to have one intermediate where because I don't think.
She said start with what?
I don't know what you're gonna say.
Okay.
I think you have to have an intermediate in between those 2 where the CX isn't together.
Okay. So break the CX bond in one step, form the C nucleophile bond in the second step. Yeah? And the arrows that I would need there show the CX bond breaking towards the X, form what intermediate? Carbocation. And then have the nucleophile attack. That's a 2-step mechanism. And when we define these substitution reactions, we define them by their kinetics. So those of you that just said you didn't like Gen Chem 2, unfortunately, Gen Chem 2 named these reactions. We named them by their kinetics. The reaction coordinate diagram that we have for option 1 here, I start at a stable set of starting materials. I need to form this reactive intermediate, and then I form my products. It is not easy to form that reactive intermediate. It's much easier to react with it. So we have these 2 steps, 2 transition states, 1 intermediate. The rate determining step is here. I'm not going to talk to you guys about that much, but it really just says, where do I need to put in the most energy to make this reaction finally happen? I need to put in the most amount of energy right away. After I've done that energy, the rest of it will just follow through. It's a roller coaster. Once I get up that biggest hill, the rest of it is smooth flowing. And in this mechanism, the rate determining step involved how many molecules? The nucleophile played no role. Correct? The nucleophile just watched. And then after that first step was done, then the nucleophile played a role. So this first step we call unimolecular. It only involves the alkyl halide breaking apart. So this reaction involves a nucleophile substituting in a first order mechanism. Unimolecular. I don't know why I closed that bracket. Meaning first order. It depends on one compound and one compound alone, the alkyl halide. If I have more alkyl halide present, there's more likelihood of me going over this activation barrier at any given time. My reaction happens faster. If I add more nucleophile, my reaction stays at the same pace because the nucleophile doesn't play a role in the rate determining step. So we call option 1, which you guys figured out, we call this Sn1, first order nucleophilic substitution. It is named backwards from how it's spelt. Sn1, first order nucleophilic substitution. That's our Sn1 mechanism. The Sn1 mechanism involves a carbocation intermediate. Always, full stop. Do I really need to form a carbocation intermediate? Is there any reason that I can't form the nucleophiles bond first, have a different type of intermediate, and then break the bond to the chlorine, the halogen? What do you think about that? I see some grimaces. You don't like it? Salem doesn't like it either. I did it in reverse. Is that fair? Like instead of breaking the bond and then forming, I formed the bond and then broke it. I what? There's a lot going on. Well, I'll tell you what, I forgot something, and that is the negative charge has to be consistent. Okay, there's a lot going on. What else? Oh, yeah. Did you guys catch that? Say it louder. That's a Texas carbon. That is its published literature name because everything is bigger in Texas, including the number of bonds that carbon can make. Cannot exist.
Is there any way that the nucleophile just like bonds as soon as the other one, so it's like
Kind of like that video I showed you guys. So that's option 3. Option 2 is not an option. I just wanted to show you the ridiculousness of it. But the plausibility, right? I need to break a bond and form a bond. What order do I do it in? Does it matter? Yes, it does matter. You could break a bond and then form one, but you can't form one and then break. Or, as Jordan suggested, option 3, my nucleophile forms a bond as my halogen leaves. Both of them happen at the same time. And the reaction coordinate diagram for this, it looks very simple. I go through one transition state, which means it is the rate determining step. There's only one step. And how many molecules are needed for that rate determining step to happen? 2. I need the alkyl halide and the nucleophile. We call this bimolecular or second order, because if I change the concentration of nucleophile, my reaction happens faster. If I change the concentration of alkyl halide, the reaction happens faster. If I change the concentration of both, it happens faster. We can go back to Gen Chem 2 and talk about the math and the kinetics. It's really fun. I did it one semester, just a little outside of everything else we're going to do. So we call this Sn2. Second order nucleophilic substitution.
okay, so it's bimolecular because you need both molecules. That one's unimolecular because only the halide, carbohalide is involved.
Yep. Both molecules are needed in the rate determining step. There's only one step. So that step determines how fast the reaction happens. But this reaction only needs the alkyl halide to form the carbocation. That is the rate determining step. If in an alternate universe this were the rate determining step, then it would also be bimolecular. But this happens much, much more quickly. This is much, much easier to do than this.
And then what causes the difference in the order, like first order and second order?
How many molecules are involved in that rate determining step? Unimolecular is what we call first order. Bimolecular is what we call second order. Those are synonymous, interchangeable. So,
I assume we're gonna go over it, but like, how do you know?
yes, yeah, we are going to go over it. Looking back at the video, me and Bro engaging in a backside attack during Sn2, one step. Bro forms a bond while bro gets kicked off at the same time. Second order. Okay. That is substitution. It happens in two forms, Sn1 or Sn2, until we get into OChem2, and then we'll talk about more types of Sn mechanisms. Let's do a similar comparison for elimination.
So for first order, can only one bond break or one bond
At a time,
at a time? Is that like
that's not a bad way of looking at it. Do you know a lot of students, I don't want to say this because now it's going to accidentally be the only thing that sticks. A lot of students think Sn1, one step, Sn2, two steps, but it is exactly the opposite. So that's a good way of saying it, which is Sn1, one bond at a time. Sn2, two bonds at once, two changes at once. It's a good way of saying it. Okay, let's start with our alkyl halide again. And let's react it this time with a base, which we've already decided if it's a nucleophile, it's also a base. It's just going to play a slightly different role. So I do have to clarify that, actually, sorry, our structure will now need to highlight two carbons. The full name of elimination, by the way, is beta hydrogen elimination. And remember, that is simply a description of the two carbons being adjacent to each other. Alpha has a group that will leave, the halogens, and beta has a hydrogen that can come. And the product of our elimination we get a conjugate acid, the base that has taken the hydrogen. We get an alkene because the alkyl halide has behaved as a base. And we get this leaving group. We have our halide has left. How many ways can I do this? Well, let's analyze again what needs to change. I need to break a CH bond and a CX bond. I need to form a CC double bond, a base to hydrogen bond. There's a few different options here about what needs to be done first. Do you guys want to offer any suggestions? What sequence might we go in? What changes could you suppose happen at the same time? The two bonds break at the same time, but no bonds form at the same time?
Yeah, the only bond forming is the carbon-carbon double bond, and that would.
Well, there is a base to hydrogen bond that forms as well. Yeah, it can form before it breaks. It could be the reason that it breaks is this bond forming. Okay. So what's your suggestion? We show the halide leaving, just like last time? And form what? A carbocation. And a halide. And now our base can come in and take a hydrogen and form an alkene. base deprotonates. Who owns the electrons between C and H? Why? More electronegative. Carbon owns these electrons. And what would good old beta carbon want to do with its electrons? Share it with alpha, who is currently electron deficient. Sweet. Here's the reaction coordinate diagram for it. Pretty nice. So let's call elimination reactions E in the same way that we called nucleophilic substitution reactions Sn. Would you label this option as E1, a first order elimination, or E2, a second order elimination? E1. My rate determining step depends only on this unimolecular production of a carbocation. This is the E1 mechanism. How often will an E1 mechanism involve a carbocation? Always. What similarity does E1 and Sn1 have in common? That was a little redundant. 2 steps, carbocation intermediate. I would really lay on the carbocation intermediate. Sn1 and E1 are sibling reactions, if you will. Those are reactions that compete with each other because they follow the same first step. So what can we expect for option 2? I'm in a weird spot on the board, so I think I'm going to kind of come over here to the right-hand side. Maybe I'll give you option 3 again. Let me give you option 2 as an option that won't work. Once again, because apparently I like doing that. We could suppose that the base does its job first, deprotonates the hydrogen, and leaves us with a negatively charged carbon. And that perhaps this is the push for the formation of the alkene and the elimination of the halogen. But the problem is we've seen this. I gave it to you just before on here. R minus. R minus. One of the most aggressive bases that we can make is a negatively charged carbon, which means that this is not easy to form. So while it may seem plausible, if this reacted, there is no conjugate acid less acidic than it. It will just rip that hydrogen right back. So it is plausible, but it's not, sorry, it's pushable. We can show it. Thanks for stopping by. But we can't assume that it's plausible. There's no way that this conjugate base will exist. So what's our third option? What's the only other thing that we can do to make our final product? Say that again. How can I do it all at once? A lot of arrows. Well said. Base takes the hydrogen. CH shares the electrons to make CC double bond. And CX breaks to X. How many steps? Just one. How many molecules involved in that step? 2. Bimolecular. So we should name this E2. Beautiful. A sibling reaction to the Sn2. Competition between Sn2 and E2 will occur because they are very similar to each other.
Why did you give us this? The R minus, if it like doesn't happen.
It does happen.
Oh, okay.
It's just very hard to, and if you're not careful, it will explode. The thing is, it's very hard to make. In fact, we'll talk about this in OChem too, but generally the way you make it is take an alkyl halide and react it with magnesium, elemental metal. And the magnesium gives electrons to this system and creates an ionic pair between them. So the magnesium stabilizes the R minus just enough that it doesn't rip away just any hydrogen. But if it's in something even slightly acidic, it'll take that away. All right, so we've got 4 new reactions, Sn1 and E1, Sn2 and E2. What type of alkyl halide? You'll notice on this table that I've got methyl, primary, secondary, tertiary. What type of alkyl halides are set up well to do E1 and Sn1 reactions? What type of carbon substitution would do well at Sn1 and E1 reactions? The bottom 2, because they're more substituted. So they have more stable carbocations. And what type of carbon substitutions would do well at Sn2 or E2? Yeah, kind of, except methyl doesn't have a beta carbon, which means that it can't do elimination at all. But because there's very low steric strain, it makes it much easier for a base to come in and take a hydrogen, or for a nucleophile to come in and kick out another group. I have some more videos. Here's Sn1. That's bromocyclohexane up there. And he said, I'm not going to be able to climb up here with how heavy bromine is. Throws off the bromine and keeps chugging. This one's not the best, I'll admit. Like, you really got to anthropomorphize the molecule, and I'm not sure the struggle really makes sense, but you can kind of see how that rate determining step depends only on it getting rid of its halogen. Okay, I have another one. This one is maybe my favorite. Kicks them out. We're actually going to talk more about the stereochemistry when we come back next week. I need to teach you guys about how Sn1 and Sn2 have very different effects on chiral carbons, because Sn1 involves a flat carbocation with no chirality. Prochiral, meaning either configuration can be made. And Sn2 is stereospecific. It comes in and it has to attack directly opposite where the leaving group is, which means I'm essentially changing the position of 2 of my bonds. That changes my absolute configuration. So this like depiction of a nucleophile kicking the leaving group out directly opposite, that's legitimate. It's going to have this umbrella effect on the chiral configuration. In fact, if you were to take this analogy of kicking someone out of a car for Sn1, it would be more like coming to the side the guy's on, pulling him out, and then getting in on either side of the empty taxi seat. Make an R chiral carbon or an S chiral carbon. I think I have another one, but no, that was it. Just my 3. You can actually see in this original one how it's a backside attack as well. It comes in directly opposite from where it's leaving. That is actually supported by molecular orbital theory. The nucleophile needs to attack the sigma star orbital. It needs to break the bond between carbon and the halogen, and that means coming in directly opposite from where it is. Okay, one of the last things I wanted to show you guys was a new resource I've added to your external resources page. I got this at the conference and I kept forgetting to investigate it more and see how useful it was. So there's a link to this on your external resources, one of the top links on your homepage. I did put it towards the bottom for now. Endless practice problems. Someone was asking me for more practice problems. Someone is always asking me for more practice problems. They are AI guided, so you have to take that with a grain of salt, but it is incredible what it can do. Here is practicing stereoisomer relationships. Okay, well that was really easy. Those two are obviously the same. This has a lot of different channels. So you can look at organic stuff, general chemistry, and things that have been published. I do want to say though, if there's a topic that you run across that doesn't look familiar, it might be OChem 2. Ignore it. It's just dangerous to say because maybe it doesn't look familiar because you haven't studied it enough. But if you're interested in IUPAC nomenclature, functional groups, resonance contributions, I'm not going to lie, I got most of the resonance contribution one wrong. So I'm not sure that I trust it. It doesn't, first of all, the options it was giving didn't make any sense. These resonance forms are terrible. These are terrible, terrible resonance forms for this structure. So I don't really like that one. But here's a cool one. It gives you 2 resonance forms, and it wants you to draw on the left structure to form the right structure. I actually kind of like this drawing tool that it has. So you can see I need to form a CO double bond. So I start from the oxygen and I just drag a line, and then it auto corrects the shape. I need to move this double bond. If I can do anything I want to, but you can see that it's giving me specific spots to go to. So as long as I go to a specific spot, it just fixes it. And then you can check it. Okay. It didn't like that I sent the pi bond to the other atom. It wanted me to send the pi bond to the other bond. Sure. I would have accepted either. There are some things, though, that I do not like what it does. For instance, if you ever have to draw an arrow starting from a lone pair. Oh, I wish I had stayed on that one. It does not show you a lone pair. And instead, what it will have you do is draw an arrow from the atom itself. I don't like that. I want you to show all relevant lone pairs. I don't ever want to see an arrow that starts at an atom. Arrows don't start at atoms, they start at electrons. And the atom is a representation of the nucleus. The symbol is a representation of the nucleus, not the electrons. So there's one, that's my main flaw with it, but otherwise, chair conformations, stereochemistry, meso compounds, molecular relationships, find the acidic proton, draw mechanism arrows. Use it to your advantage, practice with it. It's a really great resource. Okay, I'll let you guys go early. 3 minutes, wow. And I want you guys to be thinking about how those reactions we learned about will fit into this table. How does something being good at being a base, but not working with a carbocation forming structure, how does that help you predict what's going to happen? We'll fill that in first thing Monday. We'll look at mechanisms in stereochemistry, and then we'll move on to our last little stuff. See you guys Monday. You too. We're almost done.